no medium, it's not air, it's not sound, it's not the physics that goes into elastic, it's much simpler. So you have the free space, and in the free space you have the propagation of radio frequency. This is very important because this lesson will be based upon the generation and the exchange of heat, of energy, and the exchange of energy, like from the sun, uses electromagnetic wave. So if you use electromagnetic wave, you must be subject to Maxwell equation. So Maxwell equation, if you have no source, and you have homogeneous medium, it means that you are in the space, for example, or you are in a uniform medium in the 3D, then the simplest way of Maxwell is a wave equation. It means that any signal that propagates in the space, okay, in the empty space, or in a space with constant propagation velocity, should be a solution of this equation. So any electromagnetic signal that you can measure in any possible position of the space and in any time, I put T as a core argument, so this is a signal that propagates moving the space and the time, should be a solution of the wave equation that tells you that the second derivative of this signal with respect to all the coordinates, all the space coordinates. So okay, this is proportional to the second derivative of the space of the signal with respect of time. And the proportional go to a constant that is the velocity of propagation. I put C because in the empty space the velocity of propagation, we know, is the maximum possible. In all other space is lower, is 300,000 kilometers per second. Okay? So remember that as far as the medium is homogeneous, this equation is good. So it's good also for sound, apart from the fact that in sound you have to put the velocity of propagation of the sound. So since this is the light speed in vacuum, of course the sound is much lower. Okay, we'll see later. And the point is that this solution can also can write it in this way. This is a more compact way to write. So you use this operator that is the derivative with respect to space. Sometimes you find that this operator delta square, it's an inverse delta square, and this is just the same way as written. But this is a very complex equation. It's not so easy to understand. However, there is a very simple solution of this equation that are plane waves. Okay? This is a linear, it's a differential equation, so it's linear. And plane waves are a linear solution, a solution to this equation. Since this equation is linear, it applies the superposition of effects. It means that if a plane wave is a solution, any solution can be expressed as a combination of plane wave. Okay? So what is a plane wave? A plane wave is a complex exponential. So it's a wave that I can write in this way is a complex exponential that will comment here, 2 pi f0 x plus x of 2 pi f0 y plus x of j 2 pi f0 z plus x of j minus 2 pi f0 t. Okay? This is the more complete function of a complex exponential. Someone of you can remember that this was in the Fourier transform. The Fourier transform uses this. That is why plane wave, for example, are very popular for us, because you have a very powerful instrument, that is Fourier transform, to obtain a decomposition of any wave field into a sort of plane wave. Okay, what is it, a plane wave? It's very, very simple, just to give you an idea. If you have, for example, a charge that emits a field, this charge emits a field that increases with the sphere. So it propagates in the sphere. Okay? A plane wave, what is this that I designed? These are all the points in which at a certain particular time the field is constant. Okay? And this is called wavefront. It's like when you are going on a surf on the sea and you see a wave. And you see the wave, and you see on the top of the wave the elevation is constant. This is a wavefront. However, since this wave is traveling, because these are electromagnetic fields that move in this time, this wavefront moves time. So this signal that is here, after some time, moves in this position and so on. What is the mover? It's written in this part of the equation because this is time dependent. Okay? And this is not plane, because here you see the wavefront is curved, but it's very easy that you can write the wavefront curve as a superposition of the plane wave, as a sphere can put as a sum of plane wave is locally tangent to the sphere. So you have a plane wave that is this is another plane wave, and this is another plane. So plane wave is a very simple, and it can be used also to handle very complex signal, because you can put many plane waves. So why this is a propagation? First of all, let us do in a simplest way. So let us look at how is in the 1D. Of course, this is impossible to have a signal in the 1D, because we are in the 3D. But if the 1D domain, every equation would be simple, because I have written this one. Okay, and the equivalent solution, so the equivalent to this in 1D would be only a function of x and t. So we are looking at the field. I'm just trying to make it simple, because now I can represent my electromagnetic signal that change with the position and with time. You just take this and this, okay? And if you want to make even simpler, you take the real part that is the cosine. So the general is xj 2 pi f 0x x minus f0t multiplied by t. Okay, I put together this and I put 2 pi after. But I can take, for example, the real part of this plane wave that is a cosinus. Just if you understand better cosinus, this cosinus 2 pi f0x x minus, let us call f0t t. Okay? Okay. Well, what is this? let us write in another way. Let us write in cosinus of 2 pi. Let us take the f0x outside the 2 pi, and you put x minus f0t divided by f0 x multiplied by there is a bit that is I was missing a bit here. 2 pi f0t, this is correct. Okay, it's correct. Okay. Here, this is a velocity of propagation. Is exactly this ratio. Okay. So this is x minus v multiplied by t. Okay? So let us look at this. I adjust it next to this. First of all, v actually is chi if you consider the space. So chi multiplied by f0x is f0t. It's what I call f0t. And this equation is cosinus of 2 pi f0x x minus chi multiplied by t. Okay? What is this written in this way? If you write it in this way, it means that, for example, at t equals to 0, you have a pure cosinusoid. Okay? This is what you write for t equals to 0. Start of time, you say cosinusoid. Okay? And what is the spatial period of the cosinusoid? So the distance between the wavefront. The distance between the wavefront is the inverse of the period. That is 1 divided by f0x. Okay? So this distance, this, is 1 divided by f0x. This is expressed, so if x is in meter, this is a number of meter. It's the number of meters that you have in one cycle of your wave. So this measure, it's what I call meter per cycle. Okay. Actually, the cycle is not dimensional. So this quantity is meter as a dimension. But the meaning is how many meters there are in your cycle of the wavelength. Okay? And so what is f0x? So the terms that you have here, the f0x is just the opposite, is cycle per meter. So is okay? How many cycles you make in 1 meter? Okay? You understand? This is just at the beginning of the time. I have this. Now I say start time, time evolve. What is this operator if you remember signal theory? If I write x minus something, what I should design? So what does this operator do? Shift, right or left? Right. So when I write this, it means that when time passes, okay, when time passes, after some time, my waveform is now here. Okay? Because it's moved by what? This moved by c multiplied by t after a certain period. Okay? So this is a time shift. So this wave is this, but after some time, this is this is this, and the wave moves in this direction. Okay? So if you write in this minus field, the wave is moving from the right, from the left to the right. Okay? It's moving in the positive direction of x. Okay? Of course, you can also put also a plus. Okay? But if you put a plus in the waveform, the wave is moving in the opposite direction to the left, or from this point to this. So if you are here and you're emitting a field that goes into some object, then you have to put the minus sign. And usually, since you transmit a signal, you put the minus sign. Okay? Well, what is this ft? Okay, f0t. Well, this is f0x is cycles per meter. So this is cycle per meter. Okay, and the c is a meter per second. So you multiply by meter per second. Okay, so if you multiply the cycle per meter by meter per second, you get the cycle per second. So this is really the frequency. It means that if instead of fixing the t, you fix the space, you always look here, then as the wave propagates, you see, you get the signal, but after some time, this signal goes here, okay? And this f expresses how many cycles you make by second. So the time that you make to do a cycle is the inverse of this, okay? So this is called spatial frequency, okay? F0x is called spatial frequency. Okay? The number of cycles that are in 1 meter, and we will use it very much. Okay? Then there is another definition that is the inverse of the f0x, that is lambda. Lambda is the length of a cycle. It's called wavelength. Okay? So the first spatial frequency, wavelength, that is the inverse. And now there is the third quantity that we have introduced, that is f0t. But usually this is called f0. I put a t to remember that these are cycles per second. Okay? That is the frequency. Tells you how much faster the waveform is pulsing. So if you look only the position 0 and your waveform move, how much faster you see a top of the waveform in 1 second. If you see many tops of the waveform in 1 second, this move very fast. Okay? And this is the propagation. Okay? Of course, they are linked. So lambda is c divided by f0, and this is a very important property. Dimensionally, always when you write this, remember that this is written in meter, okay? This is meter per second, and this is 1 over second. So this equation is correct. Okay, remember always to do it. For some of you, this spatial frequency, that is inverse of the wavelength, and the frequency are very clear, but I wanted to summarize it again. So this waveform, it's a plane waveform, so you understand, so it moves, it is this in the space, so in the space you see, it's like when you have a C, you remember when you have a C and you see this wave on the C, okay? This wave has some peak, but now with time this peak moves in some direction, so the wave also moves, and the same effect is seen in a different direction. The point is that we are only considering the 1D. So what is a waveform, for example, a plane waveform in the 2-dimensional or in the 3-dimensional, and so on. Okay? So I can represent easily the concept in the 2D, and the extension of the 3D is not so difficult. But it's always the same concept. When you consider the 2D, you have a solution of this equation. So you don't have this part, but you have a solution of it. And the solution will be a field that now depends on x, y, and of course the space, time, okay, that will be written in this way. Then you have a spatial frequency along x, okay, a spatial frequency along y, okay, and you have the propagation in time. Okay. Now I think that this is just the first lesson, but maybe that you just interpret, you can interpret it. These are the number of cycles per meter in one direction. These are the number of cycles per meter in the other direction, and this is the number of cycles per second. So the point is how this appears. Again, this is complicated. But if you put it in only one exponential, this plus this minus this, and you put the real part, okay, you have to write a bidimensional cosinusoid. Okay. Remember that I put the negative because I want something that propagates from the origin upward. Okay? So, how this wave will appear in the bidimensional space? Well, this wave appears in the bidimensional space, difficult to represent. It's like when you see, let us say, a wave at the roof. Sometimes you see Ethernet, for example, an Ethernet roof. You remember that are made in this way. So I will try to, an Ethernet roof, it's a roof that has its top here. I can represent only in, I'm not good at all in make picture. I can represent as seen on the top. And seen on the top you have the ondulation of the roof that are so. So it means that along some direction the roof is constant. In some direction you have a maximum, in some direction you have a zero, in some direction you have a minimum. And since the signal is periodic, these are, for example, all the points in which you have one. So this is all the top, then you have a minimum, another top, a minimum, another top. Okay. And of course, this is a wave, okay? You can measure as a physical representation of this, and this by looking this. This is x and y. You don't have the dimension of time because now time is 0. And then you see that here you have the distance between two of the top is exactly like measuring this distance, okay? Because if you cut in this direction, you exactly see one sinusoid. But the frequency of your sinusoid is the length, this is lambda x, is 1 divided by 0. Now you have two different wavelengths, because you have a wavelength here and a wavelength here, okay? And this is, of course, lambda y. Why? Because you have in a plane, and then basically you can do two things. Or you define this and this, or you can say that I define a direction in which the wavelength is minima, okay, because this is the direction of minimum, and you say what is the direction, okay? But of course, always two parameters, you have to define the wave. So the wave is just a roof at the top, okay, in the two-dimension, and as it's a two-dimension, you have to derive where is the direction of propagation, that is an angle, and which is the wavelength in this direction. In this direction, this is wavelength, is lambda, okay? How lambda is related to lambda x and to lambda y? This is to be understood when you move the time, because lambda has to do with propagation, okay? So now, if you start the time, you see these wavelengths, so this constant top of the roof are moving in this direction with time. So you see this wavelength propagating in this direction. So you see the oscillation that shift in this direction, because this is a positive direction in the two-axis. Okay? And this is a positive propagating plane. Remember that if you consider as a part of the 3D, all plane orthogonal to this, the field is constant. And so this is a wavefront. And this is a wavefront in the 2D is a line. But if it is the 3D with this, the z-axis, it would be a plane. So you understand that in the real 3D, the wavefront is plane. So a plane wave is a wavefront, a wave that a wavefront so this that is propagating in this direction. Okay? So you just define the wavefront, and the propagation is orthogonal to the wavefront. As this is a line, and you see the propagation going in this direction. Okay? This is how the wave, and there is an important property that should apply, that is the frequency, the extension of the previous, that is the frequency F0. F0 is, remember, the number of cycles that you make in a second. So if you measure with time, you see this wave is moving, so you see this point, now it is a 0, then when comes this is a point, up, down. So if you measure in time, you see the intensity of the field going up and down, up and down, up and down. And if you say how many cycles I do, the cycles are ruled by this C multiply f0 xy plus f0 squared. Okay, that is a very simple equation. And of course, this is also as f0, remember, f0 is c divided by lambda. Okay, you remember it was written there. So the inverse of the cycle. So it's always true from this that 1 over lambda is the square root of 1 over lambda x squared plus 1 over lambda y squared. I do not show you the demonstration, but if you want to measure this length, okay, for the sinusoid, you will see that the inverse of this is the square root of the inverse of this plus the inverse of this. It's just a matter of doing some mathematics, some passage, and so on. So in the 3D, it's nothing different from the 2D. In the 2D, I have to define two things, direction and frequency. In the 3D, I must put also the direction in the space. Okay? So when I define a plane that moves, I should provide the two angles to provide the plane. So I start from this is the first angle, and this is the second angle, and this is the plane, and then I have the direction, and then I provide the frequency. So a plane wave in the 3D is defined by actually three parameters, f0x, f0y, and f0 zeta. Okay, three parameters, because this will, of course, related to the other three. Okay, just because to define a wavefront in the 3D, you just need three numbers. You can also decide to put one angle, the other angle, and the wavelength, but it's always the same. So three parameters describe completely the propagation of the wave in the field. And this is that. So wave fields are not different from this. Okay? But what is important to understand from this, that this applies to sound, and this applies to sonar, and this applies to radar, the same. What's the difference? The difference is that in this equation, in sonar, you don't have to put the velocity of speed in vacuum, but you have to put the velocity of the wave in the pressure wave in the actual medium. Let us do some example, because I want that you have clear the number, what you're speaking about, what is the number of times. First of all, why it is important, the wavelength? We will see in a moment with the emission on board. But I can just say that if you have a body that emits, okay, it emits a wavelength. Since here you have a body, for example, a piece of metal, it emits a wavelength like moving an electrical field that passes in this body, but at the edges, since you don't have any continuation, the electrical field, the current is zero, and also the electromagnetic field is zero. So you can emit this frequency, you can emit this wavelength, you can emit higher frequency, but you must fulfill boundary condition if this is aligned. So it means that basically when you have an object, the minimum, the higher, the longer wavelength, that is the minimum frequency, so the frequency should be, if this body is L, should be, the frequency is 12, so it should be greater than 1 over 12, okay? So you can have a higher frequency, but not lower. And this is, for example, important. So let us assume F is C divided by lambda, if you consider the space. So if you consider your smartphone, of course, this is a perfect position, because you have perfect tuned, so 0 as a string. So if you consider a smartphone, F0 is 5 gigahertz, and we want to compute lambda. Lambda is C divided by F0, so is 300 by 10 seconds power meter per second divided by 5 gigahertz. 5 gigahertz means 5, 10, 9 hertz cycle per second. So how many meter per cycle? So is 6, 9, this is 3 down. I forgot the 10 times 3 and I write in millimeter, and this is 300 divided by 3, and this is 60 millimeter. So it's 6 centimeter. Okay? It means that if I have a good adaptation, good tuning, I can have my phone that is length, okay, 3 centimeter, okay, 6 centimeter, 12 centimeter, and so on. So the minimal length in order to have an antenna is 3 centimeter. In fact, it's very difficult to see phones that are smaller than 3 centimeter, because you need an antenna. If you remember the old, very old phones, they have an external antenna. So they have the phone and the antenna was something in the range of centimeter. Now they discover that the antenna can be incorporated within the phone. So if you want to emit a signal at this frequency, to emit very well, you must, to generate a varying electromagnetic field, you must have a frequency in this order. But it's also true the opposite, that if you want to see the reflection, because now, for example, radar want to see a reflection, you can see a reflection if the wavelength is 6 centimeter, okay? If it is a wave that is very big, you don't see a reflection and the signal passes through, but it's not reflected because you cannot have a matching. Okay? So the frequency should always be matched to the size of the object you are considering. That is why, for example, I told you yesterday that the radar is cloud penetrating. Why? Because in radar you use this frequency. This frequency is 6 centimeter, and 6 centimeter is much more than the raindrop in the cloud, or the molecule of water vapor in the cloud. So the cloud is completely transparent for not this for the optic. The optical is not cloud penetrating, because in the optical you are considered that the wavelength goes up to 700. This is 400 to 700 nanometer. Okay, nanometer means million smaller than the millimeter. Okay, millimeter, micrometer, nanometer, 6 order of magnitude. So you expect that a drop of rain is huge corresponding to the nanometer. So since the water is a conductor, it's like having an antenna gets all the optical energy, or reflected, but you don't have anything. So when you consider the sound, okay, this is different because the sound is a sound pressure. Okay, the sound pressure, when I move the air periodically, I generate a wave that propagate exactly like this, and I can write in plane wave, but it's different the velocity. So, for example, if I consider ultrasound, you remember that when you speak of sound between 20 Hz and 20 kHz is a normal sound, okay? I don't think that all of you can hear the 20 kHz sound, okay? These are very, very, very high frequency. For sure, me no, because I'm too old. But when I was young, I was trying to generate sound at different frequency, and up to 18 kHz, I was able to hear. If you have never been closer to a television, but not the new one, the old one, the big one, sometimes you see a very high frequency tone. If you hear that tone, you can hear this frequency that is 15 kHz, because the frequency which the line is emitted in. It's a television, and all the television is one line is very, very fast, and they draw an entire frame, and you don't know this frame because it's moving 15,000 times in a second. So you don't see, but your brain make a lot of effort to reconstruct the signal, because actually you are looking only at moving point in an old television. So old television were very tiring. You were tired if you observe it for one day. For the new television, it is not so, because they are just continuous images. But that, when you consider that and ultrasound, and you consider the device used, for example, for location, for that are very, very cheap. If you take an SR05, you have 80 kHz. Okay. And what is now the wavelength you are considering? So what is a minimal object that can reflect? This is very important, because that chase mosquito. Mosquitoes are very small. Does this reflect the mosquitoes? Well, let us compute again the wavelengths. But now we have considered that the velocity of speed in sound in air, because it's different between the medium, the velocity in the air is 330 meters per second. Approximately this, maybe depends on the humidity, but let us use this. And if you wanted to check what is the wavelength is again velocity divided by frequency. So is 330 divided by 80. If I forget the kilohertz, the result will be millimeter. Okay. So this will be in millimeter, because it's 10 power 3, and this is 4. Okay, it's 4 millimeter. I think that is a mosquitoes compares with the 4 millimeter. Okay, so as a mosquito matches this, okay. If it is much smaller, it's impossible to see the mosquito. But as a mosquito of 4 millimeters is reasonable, and that can also increase the frequency. 80 kilohertz is a minimum. But you cannot use, for example, 40 kilohertz. That is why you don't hear of 20 kilohertz, because 20 kilohertz it will be 16 millimeters. I don't see a mosquito 16 millimeters. Okay, so this means that you don't hear bat, not because bat don't want to disturb you, but this will be not relevant for them to chase the object. So you see that these 4 millimeters actually are even better than using a smartphone in the radio frequency. That is, they are comparable with frequency. A lot of alarm, for example, alarm for battery, in many years ago were done in the ultrasound. The problem of ultrasound, you have a sharp attenuation. So the attenuation, the signal in the moving there, it makes a lot of energy. Okay, moving an electromagnetic field is not energy at all. Okay, so the signal propagates and it's not attenuated. It's attenuated only because the same energy now it's every time it's located over a sphere that becomes bigger and bigger and bigger. So the energy is conserved, but the signal you hear on a bigger surface. So this is attenuation. But in the air you have a more attenuation because to move the air you must do a work. Okay, because you are actually moving molecules. Of course, if you don't consider the air, so for example, you use tissues. Tissues means tomography or any medical activities that you do. It's the same as you sound, but in that case, tissues contain a lot of water, so it's much more rigid than the air, and if it is rigid, the velocity is faster. In fact, the velocity in the tissue can be 1,000 meters, 1,500. If you remember, well, if you have seen many of the old Western, when you have Indian that were understanding the train comes, instead of hearing the whistle of the train, they put the ear on the iron, because the medium in the iron travels 5 times faster than the medium in the space. So you hear the train 5 times before. Okay, that is good. And of course, this lambda would be the frequency typical. It's in the order of 1 megahertz. The frequency used for tomography, for emission tomography imaging, can be 10 megahertz. So it's much higher than it's ultrasound, but ultrasound. But if you want to consider what is your capability to see a very small imperfection, then you have to put also this. Lambda is 1,000 divided by 1 megahertz is this. Okay. So this in millimeter, I can take out a factor of 3, and this is 1.5 millimeter. Okay, so it's very, very, very small element that react to tissue tomography because you use a very high frequency, but fortunately also the propagation is very high. Okay, so this let us play with. This is important because when you want to do a remote sensing observation, you must match the frequency with what you want to observe. Otherwise, you don't observe that. It's very important. And the second element that is very important, if you understand this, you are in a very good position, you have learned something significant in radar, in sonar, in tissues, and so on. I will go on and speak about energy, because also energy is important, because if you have the signal is reflected, but it has no energy, you don't hear. Okay? Can I go? Do you have a question about this? Is this clear? Okay. Someone of you may do this in other course, so maybe I can do nothing more. And also for thermodynamics, because when you think about energy, you think about emitting the energy. So I'm speaking of the. Well, it's a long story. It is written in the book. So I'm really following the line of the book. So if you download the book, the link it's on the web, it's in the program of the courses, there is the internet link you can download, and I'm really following the book. I told you in the book you find much more detail. So for example, for the black body, there is the whole demonstration, maybe part of the whole demonstration, and I have to simplify. Why I consider, because all the energy comes from black body. Okay? Black body means me, you, the sun, a lamp, everything. Every body that is at a certain temperature, it's a black body. So you consider that a black body, it's a body characterized by a temperature. And if it has a temperature, it has some energy, okay? Unless you have zero temperature. So if you have some energy, then it's a problem that you must approach when you consider many black bodies together, because there is an exchange of energy. If you have energy, you emit it. Why you emit it? Of course, because you have a status of energy, and maybe if it is a lower status of energy, energy comes from Z to other. But clearly, this body cannot accumulate energy, because if you accumulate energy, you must have something that becomes hotter and hotter and hotter. And so, if you don't accumulate energy, so you don't have something that create energy from temperature, or you don't disperse energy, then you exchange energy. So you can put energy back to you, and so this is irradiation energy. I mean, you remember that heat can be transferred into 3 different ways. You remember how you can transfer heat? The first way is when you put your hand on the fire, and this is contact. Okay, direct contact. The second heat, it means when you use, for example, a fan to put a cold, and this is now it's working. Here we see the temperature is perfect. In the other room it was very hot, and this is just to use a medium that moves heat. Okay, this is circulation. And the third is electromagnetic. The difference is that when you have electromagnetic, here you get the heat from the sun, but there is no medium because there is empty space and there is no contact. So when you consider black body, they are emitting electromagnetic signals. So you hear actually a signal because they are always emitting a signal, and they are in thermal equilibrium. So no one accumulates. I write it mean in time. So instantaneously you can have a lot of accumulation of energy, but if you have a lot of accumulation of energy more than other, immediately you are the bigger, and then you exchange the energy to the other. So there is a continuous transmission, so you are transmitting an electromagnetic signal, okay, as any other. Okay? And of course a black body is a particular. So why it is a particular? It's particular because it's a perfect absorber. So it gets the signal, it gets the electromagnetic signal, okay, and it does not reflect. Okay, for example, this is not a black body. There are some white bodies, for example, are bodies that hold the energy, put back, and you see a reflect. You see white, okay, because it reflects whatever comes in, okay. And so if it is illuminated by white light, you see white body. This is black because all the light that you put is not reflected, okay. That is why it's called black. It's a perfect absorber. Also, the glass, it does not reflect, but is not a black body, because all the energy traverses the body and goes in another direction. This is glass. So it does not transmit, it does not reflect, it absorbs. Okay? If it is a perfect absorber and it does not accumulate, it means that the energy is put back, and it's put back in form of electromagnetic field. Sooner or later, thermal equilibrium goes in the medium, in average time. Sooner or later you must emit a signal. So how you can emit a signal? You use electromagnetic wave. If you are, I told you, there is a certain of boundary condition you must respect. So you can emit this frequency, okay, and you can emit a signal with this frequency. And you see these two are orthogonal, so you can have this frequency plus some amplitude and this plus some amplitude, and then you have all the multiple frequencies. Okay? This happens, of course, in the 3D. This is 1D. In 2D, it means that you can emit the signal as a form of electromagnetic signal. For example, by making a wavelength that here at the boundary should be 0. Okay? So the wavelength can be, in this position, can be a peak, but here should be 0. And you can do this by multiplying this, for example, by this wave. if you multiply this by this way, this imposes 0 here and here, this imposes 0 here and here, then you have a total signal that is emitted. This is solved this way. This wave can oscillate with time, okay? So I can write it as a sinusoid, for example. If this is nx, this is a minimum frequency, so it's 2 pi f0x x multiply the sinusoid here and the sinusoid here of 2 pi f0 y, okay, this, and then I can put x of minus j 2 pi f0, because it's a waveform that is propagated. This is not a sinusoid, as I've shown you. So this is not a plane wave. In fact, it's not plane at all. But can be written as a combination of simple plane waves, because I told you any wavefront can be written in a plane. The good part of the sinusoid is that it performs this 0 at the border, but fx, f0x, can be any multiple of, it can be any time, multiple of the minimum frequency. The minimum frequency is, of course, this 2 lambda x, 2 L. Let us say that L and L is a surface, okay, and then you have this frequency. Of course, also f0y can be a multiple of 2L. So all this combination give you a lot of possible signals that are called modes, and these possible signals are elementary signals that keeps the, for example, I can put the frequency here because now it's always 0 and 0. And all these modes are signals that are compatible to be 0 at the boundary. I'm showing you in the 2D, but the black body actually is represented in the 3D. So it's actually an extension to this where we have to put multiply by a sinus of 2 pi f0 zeta zeta, and also f0 zeta is n zeta divided by 2n. Why I show you this? Because each of a mode can disperse only a limited quantity of energy, and this was the principle of the thermodynamic. The limit quantity of energy that is associated with this mode is one mode is related to transmit an energy that is kB multiplied by T. Kb is Boltzmann constant, it's 1 over 38 joule divided by Kelvin, by the degree of Kelvin. 10 minus 23, okay? Remember that 1 joule in 1 second is 1 watt, okay? Then the amount of work that you can do if you run, for example, it can be 100 watt, something like this. So this is a very teeny power, okay? Very, very, very teeny power. So it's not even a small micro, a minimal power. But of course, you have a lot of mode because you can combine different of this, different of this, and different of this. Remember that you have always the relation that your frequency is the summation of f0x squared plus f0y squared plus f0 zeta squared. And remember that this summation is in meter. Your frequency is in meter divided by second, okay, cycles per second. This is just cycles per meter, and then you multiply by the velocity to have a meter per second. So this is a boundary. So you cannot use any combination of this, and this, because you must obey to this law. So you must put, at each frequency, you must consider that all this should sum together and do this way. So this means that, in principle, you have a lot of frequency to emit energy. Okay? If you have few energy to emit, it's enough to, you need a few mode. So it's enough to use only the longer mode. But if you have more energy, you cannot use the longer mode because the longer mode are few, and then you must use excite also the other mode because you have more and more energy to increase. Okay. And how many, let us say, energy you generate? This is the energy of the mode, okay? And then you must consider a frequency. So, for example, if you consider all the frequency up to a maximum frequency, okay, just because you have this relationship, and you consider how many modes there are, okay? Well, remember that this, and this multiplied by C is like writing C multiplies the square root of this, and this. Divided by, of course, 4L squared, okay? Because these are the possible frequency. And the point is that an x and y and zeta should be integer number, okay? So if you consider a maximum frequency, of course you can start an x and y and zeta to be 0, then you can have this 1, 0, 0, 2, 0, 0. So an x and y and zeta are all the integer number that you can place in this space. Okay? And if you limit a maximum frequency, you limit a radius, because actually this is like considering the radius of a sphere. Okay? The sum of this and this and this, don't consider it an integer. If you consider continuous, x squared plus y squared plus zeta squared is constant on a sphere. So it's just saying how many modes you have in total. You have how many integer number you have on the sphere. It's interesting to see that the integer number that you have on the sphere is proportional to the volume of the sphere. Okay? So the total number of modes is proportional to 4, 3, pi, and the radius of the sphere. So F max squared. Cube. Okay? And since each mode gives this quantity, the energy that you can create, the maximum of energy, will be proportional to the temperature and the total number of modes. Okay? So this means that the energy increases with your temperature, okay? And then, of course, in the F max there is also the size of the object and so on, but it depends on the maximum frequency. So if you increase the frequency, you can have much more dispersion of energy. And if you write this equation, actually you have the energy spectrum that comes, the power, the energy that comes with the frequency. So, if this is the number of modules, let's say, the energy, you go with a cube with frequency. It means that if you have a lot of energy, you emit also at high frequency. Because at high frequency you have a possibility to emit a lot of energy. Okay? That you remember when I was told you when you go in the infrared because you are cold, but when you become hotter and hotter and hotter, you generate much more frequency. Because it's necessary to have, if you generate much more frequency, you can dissipate much more energy. However, this that is called the classical theory of black body, it's wrong because it appears that you can emit infinite energy, okay? Because this curve actually diverges, but it's not possible to emit infinite energy. You don't see any object that is emitting infinite energy. In fact, this all this reason has been, this way of thinking, has been discussed by Planck and later replied by Einstein, in which you say it's not complete this. Then you can add another constraint. So, what is the constraint? It's a constraint provided by, you remember this, A is equal h multiplied by f. You have heard about this. So Planck is the first that tells the energy cannot be a continuous number, cannot be any number, but should, I can put it kappa, k, where k is an integer. The energy should be an integer number of the product of these two. What is this two? This is the frequency that you are considering, and h is actually, it's important to evaluate with this, what is h. I don't remember by heart, but I have written, is h is 6.62 okay, 62 multiplied joule per second. Joule per second, frequency is 1 over second, and this is energy in joule, okay? So, of course, it's a small number, but it's a small number only when f it's a reasonable number, okay? So, when f is not so big, it doesn't change anything. When f becomes very, very big, this number becomes large. And this is important because here you have a k, and k can be only an integer number. So this means that you cannot emit half of this. Or you emit 0, and so you don't have any energy emission, or you emit 1 or 2 or 3. But if you emit 1 at high frequency, you have a lot of energy. That's why when you consider the radiation at high frequencies, the gamma for example, that are very energetic, and in this case you can emit. But if you don't have a lot of energy, you cannot emit the high frequency. So if you combine this plus this limit that tells you that at least you must get this. This is called K, it's called this, say, it's called photon. Photon means that the energy is a discrete, it's like a particle, okay? You can emit 1 particle of energy, 2 particles of energy, but not half, not 1/4 of the photon. You can emit 1 photon, but if you want to generate 1 photon, you must have enough energy to build up 1 photon. So a photon depends on the frequency. So, for example, if you consider the UAV, I have made the example with the UAV, and I make other examples that are more interesting. If you consider the UAV, because at least every girl here knows what is UVA, okay? This is a lamp, okay? This is a lamp that you go because you wanted to be fanned when you go on the sea, you don't want to be white and so on. UVA and UVR, high frequency, it's the highest frequency, even higher than the light, okay? And since it's higher frequency, it has a lot of energy. In fact, take care with the UAV because as it has a lot of energy, it can destroy also. It can produce cancer, you know. So how much energy there is in the UAV? Well, it's not an enormous energy, but it's not nothing that you can neglect. In fact, if you put the frequency that are, for example, the UAV easier. The UAV is 400 nanometer, okay? Remember what I told you today. Light visible goes from 200 to 700, okay? So 700 is the limit. After 700 you're speaking of infrared, okay? But this is a high frequency, okay? Small wavelength, high frequency. So the frequency of a UAV is clearly 300 million meter per second, 300 million meter per second, divided by 400, but nano is 10 minus 9. Minus 9 becomes a plus 9, plus 6, and this is all close to 1. Because 300 divided by 400 does not change with respect to 1, but the multiplication is important, is 10 over 15, and this is the frequency, and if you multiply by this, okay, it means that a single photon has the energy of 6 multiplied 10 minus 34 multiply 10 plus 15 joule. Okay? So a single UV photon is 10, 34 divided by 15 is another 19. Okay? Okay? Well, this photon travels very, very fast, okay? So you can say that 1 joule is 1 watt, 1 second, okay? If you consider not that you get only 1 UAV every second, but you can have any picosecond, well, this number, minus, of course, okay? Otherwise, it will be a lot of energy. It will be a catastrophe. So a minus. But if you consider in 1 picosecond, it's 10 minus 7 watt. So you are 0.1 microwatt in 1 picosecond. If you get 1 ray every picosecond, okay? So it's a very small power, but still it is a significant power. But if you consider, for example, other gamma rays. Gamma rays are very, very small, and so they have very high frequency, are even smaller than the atom, and this frequency is 10 powers 20. So, with respect to this, is 5 times higher frequency than the UAV. 5 times is a huge difference, and of course this means that they have, you see, 5 times the energy, because the relation is linear. Okay, 5 times, not 5 times, but 10 5 is 100,000. So 1 photon in the gamma is 100,000 more energy than 1 photon in the UAV. And in any case, a photon is a UAV that has this frequency. well, you remember, for example, you are very worried of your telephone, but your telephone works in gigahertz. Okay, this is gigahertz. So one UAV, one photon is a UAV, it's 1 million more energy than the photon in your telephone. Okay. So of course the telephone is not so highly energetic. Okay. And when you consider the gamma, that is 10,000, and you understand why gamma is very dangerous. Potentially, these are very, very high energy. So this means that we combine the fact that you must have at least one photon and the energy seems to diverge with the frequency. Now at high frequency the energy goes to zero because it's limited by this relation. So when the frequency goes to infinite, you need infinite frequency, infinite energy, but no one has infinite energy. And then you can write a final equation that if you want to hold the demonstration are on Wikipedia, not even in my book, but because I'm not interested in this. But then you get Planck law. So Planck tells you the energy, the power spectrum. Okay, right here. I have some time. So I have three basic frequency relationships in thermodynamic, and this is related to the black body. Okay. So it's Planck, Boltzmann, and the first relation is Planck. Everything you derive from Planck. Planck law tells you how much energy spectrum you generate in each frequency. So it's a power spectrum. It's a power that depends on the frequency divided by the frequency and divided by the surface, the total emitting surface. So you have the black body that has an emitter surface A, okay, and you say how much energy is generating if I look at some frequency. So this is 2 pi f squared divided by c. This is the immediate derivation of this law. This just comes from the derivative of energy with respect of time, that is power, and then you multiply by a correction factor that is the Planck. This is HF multiplied by A divided HF divided by HT. So with this is a quantistic correction. Quantistic because it says energy is quantized. But this happens only when you have a lot of energy. Okay? And this is a classical term. So this means that if you represent the Planck law in terms of frequency, this is a power spectrum. So if it is a power spectrum divided by a surface, what would be its dimension? Power spectrum is this is frequency. Okay, so at a certain frequency, this is approximately what Planck says. At the certain frequency, what it does express? A power spectrum is which magnitude is a power spectrum? It's a power. What magnitude? What dimension is a power?
It's watt per hertz.
Watt per hertz, of course. So it could not be different than watt per hertz, and of course divided by square meter. This means that if the body is bigger, it emits more. Of course, this is why reason. So if you want to compute the energy in a bandwidth that you receive, for example, you receive only, the ice receive only a particular band, you just integrate the power spectrum in your bandwidth, and then you have a total energy. So watt divided by square meter. Okay? And the simplest way that you can do, I can compute all the power emitted by. So, what is the dependence of this? What do you need to know of this equation to compute the power spectrum? Which number you need to know?
Frequency.
Only one.
Frequency.
Yes, of course, because you are considering the frequency. But depend on which number. So what does make this function change to be so, and so on? Temperature. So remember that the power spectrum depends only on the temperature of the power. Okay? And it emits more if it is at lower temperature. If I write you not in function of frequency, but in function of lambda, that is 1 over frequency, you have the graph that you were looking in the first lesson. So you remember that the graph were written in this way. For example, this was the graph of the sun, and this was the graph of the earth. Okay? So it says that just because the sun is at the sun and the earth is at the earth, so since the earth is colder, it emits at higher wavelengths at a lower frequency. Okay? If the sun is hotter, it emits at a higher frequency. To have the same emission of the sun, it's impossible. Okay? So you remember that anyone wants the lamp that used for example, for agriculture. If you wanted to have your agriculture at home, you should have a lamp with the sun spectrum. Of course, it's very difficult because to emit as the sun, you must have the temperature of the sun. Okay, like the left line. Emitting energy exactly as the sun emits, you must have then 6,000 Kelvin, that is the temperature of the sun. But the temperature is hidden here, but however, if you consider HF divided by KT, this is a very big number. So if this number is much smaller than 1, remember that this is approximation for small number of ALX. So ALX is 1 plus x. So this means that is 1 plus this minus 1. So this becomes to be 2 pi f squared divided by c squared. And then here you have HF, and down HF divided by KT, you only have KT. Okay? This is very simple to interpret because this is a number of mode, exact frequency, mode per frequency, and this is the energy associated with this mode. So this is a classical equation. So the classical equation works in a range of frequency in which it is this. In frequency, in wavelength is this range of frequency, in frequency is this range. So the classical works at a long wavelength. For example, in radar, okay? For example, in radio you can apply this relationship. That is this energy emitted by an antenna. An antenna is a black body, okay? And this depends on the temperature. If you put higher temperature, the antenna emit higher energy, of course, because it must disperse. And if you consider this number becomes 1 when you are in the terahertz. Or the terahertz corresponding to the 15 micron. 15 micron you are in the far infrared. So up to the far infrared you can consider this equation. That is very simple. Says that the energy is proportional, it's a parabola. It's proportional with the square of the frequency. And, of course, the temperature. When you go to higher than microwave, then you must account for the completely quantistic correction that was introduced by Planck, and this is work of Planck. But it's interesting to understand that as is a function of temperature, you can also integrate the whole power spectrum and you provide the total energy that body emits in whatever the frequency. So you just have to integrate this, okay? And the integral of this over the frequency is not very complicated. It's very, very simple. And it's the total energy. So this is what we call Boltzmann law. Boltzmann law says that the total power divided by the surface, okay, the bigger the is sigma T4. So it's very, very, very simple. It's the 4th power of temperature. The power increases very much with the temperature. And the sigma is, of course, Boltzmann constant. And just comes from the integration of this all over the frequency. And the constant is this value. And then you can derive this, of course, is total is watt per square meter. Okay, so this should be watt divided per square meter and then divided by the full power of the temperature as a dimension. Okay, it means that sigma before it's a watt per square meter. So it's how we do it. Okay? So the free law of thermodynamics will do a lot of interesting example and application. All the rule of exchange terms. So why you are at this temperature? Because we get temperature from the sun. How much the sun emits, depending on the size of the sun. So just the radius of the sun and the temperature of the sun, you immediately can compute the power of the sun. But you say how much you can compute the temperature of the sun. You can't go with the thermometer of the sun, of course. And there is another law that is very simple that says, okay, since this is a completely determined equation, okay, that depends only on the temperature, it means that if you change the temperature, the equation changes. Okay, then it means that you have a maximum of emission. So you have a frequency when there is a maximum emission of energy, and this maximum actually depends only on this equation has a maximum. Okay, this equation depends only on t. The maximum should depend only on t. So, and you get, so if you find, how you can find the maximum? You can find the derivative, okay,
Equal to 0.
divided by f, okay, equals to 0, okay. So if you do this in this equation, you get a number that is f max is approximately for the temperature in this number. And this is the third law of thermodynamics. Okay, this is called the Wien law. It seems a very simple observation, but Wien took the Nobel Prize for this. Why took the Nobel Prize? Because if you measure the maximum just by having a spectroscope, so you look all the sun spectra, you see what is the maximum, okay, at which frequency, and you immediately measure the temperature of the sun. So it won the Nobel Prize, but it told you I can measure the temperature of the sun without putting your finger on the sun or your instrument on the sun. Okay? And in fact, if we do this, we can evaluate, for example, why we are at a certain temperature. It's not so difficult, it's just a consequence of this. Why we are at a certain temperature? Because if you do a spectrography analysis of the sun, that is not really a perfect black body, but it's very close to a perfect black body, you find out that the temperature of the sun is very close to this number, 5000 Kelvin. Okay? Then immediately you have the sun, and here is the Earth. Okay? Immediately you can derive what is the power, the total power emitted by the sun. Because the total power emitted by the sun, remember Boltzmann say, the power divided by the emitting surface is sigma T4. Okay? Correct? Well, the total power of the sun should be sigma T4, so where T is the sun, okay, that I know, multiplied by the surface of the sun. How we can compute the surface? If the sun is a sphere, the surface of the circle, because if you look from the Earth, you see the surface is a circle. You remember how is the equation of the surface of the circle? 4 pi radius of the sun squared. Okay? Then all these numbers are known. This is Boltzmann constant, temperature of the sun. It was measured by looking at the maximum and using a window, and then the radius of the sun that you know. And this comes to be a huge power.
Yeah, I think
it's a number 1026 is billion. So billion of billion of billion. So the total power emitted by the sun is very, very big, but we are very happy that we are very far from the sun. So we are at a distance d. Okay? So the answer is how much power we get on the Earth. So what is the temperature of the Earth? We do the opposite. To measure the temperature of the Earth, we use Boltzmann once that we know how much power we have on the Earth and, of course, the area of the Earth. So how much power you expect to have on the Earth? Let us see if you are good in this exercise. How much power do you expect to have? We have the total power emitted by the sun, but of course the sun emits the power isotropically. Isotropically in the space, okay? So this means that at the distance d, okay, the distance d, the power of the sun divided by the element of surface, okay, how can be? How can be the power of the sun? This is the power, the total power, okay? Is the total power, okay, divided by what is the total surface of the sphere? 4 pi r, that is d squared, okay? So the power divided by surface is p s divided by 4 pi d squared, okay? This is the elementary power that you find here on a unit surface. So what is the power that you have on the Earth? Is the elementary power, so the power of the sun, that is this number, divided by 4 pi d squared, that is surface, multiplied by how much surface you get on the Earth. Okay? And the surface you get on the Earth is the surface of the circle. Okay? Is pi r squared. Okay? So here you have pi simplified. So if you do power divided by sum divided by the square root of the distance, okay? The distance is huge. Okay? It's 500,000 kilometers. No, sorry. No, it's not this. It's much huger. It's 149 million kilometers. Okay? And the radius of the Earth, you know, it's this in kilometer, 6,000 kilometers. Okay? Remember that the circle of the Earth is 40,000 kilometers. Okay? So if you put this, you can get divided by the square, and there is a 4, and you multiply by this, then you get a number. Okay? So this number is the total power that you get on the Earth. Okay? I have not this number, you can compute, but it's not finished, because if you want to compute now the temperature, okay, remember that is the total power you remember to the Earth, and you use this equation. The power of the Earth divided by the area is sigma T4. Okay? So this means that T, the temperature of the Earth, is the 4 square root of the power that you get on the Earth, that is this number. Okay? Divided by sigma and divided by area, that is pi r squared. And if you put this, you get very close to 300 Kelvin. Not you get 300 Kelvin, you get a number lower than this. You get 280, 209, but very close to 300 is the average temperature on the Earth. And this is just an exercise, as you say. It started from to understand how much temperature you have on any planet, you can do this evaluation. Because the temperature on any planet starts from how much power is generated by that body. You can compute the power if you know the temperature and, of course, the size of the body. Qui, first of all, you find the radiator power. All this power is radiated and is also resided by the other stars and so on, because it's in thermal equilibrium. Actually, it's not in thermal equilibrium because the star is going colding, and will switch off, but this happens in millions of years, so we can consider a thermal equilibrium. Then, if this is a total radiation, we can compute the power of the Earth, saying that we divide by the power by the sphere at the distance this, and then we multiply by the surface of the Earth. By the way, if we don't multiply by the surface of the Earth, we get a very interesting number, that is how much power we get per surface, and the total power that we get per surface is in the order of right here, if I remember, is 1,000. The power that you get on the Earth divided by the area is 1,400 watts per square meter. Okay? That means that ideally, because we don't have the atmosphere in this, atmosphere changes so much that if you put 1 square meter, not 1,300, 400, sorry, there is not 1,400, but 1 square meter of surface will be 400 watts. Okay, 1 square meter of surface orthogonal to the sun would be 400 watts. It's not so good because you are in atmosphere, you get lower than this, but it would be outside the atmosphere, and if you put a surface perpendicular, this would be the energy, and you just compute by this equation. So this is just an example that I wanted to introduce now to make some concrete result out of our irradiation, wavelength, and energy production. But then when you control the production of the energy and the propagation, you control a lot in the radar and in the electromagnetic field.